Okay, I'm going to show you how to find the electric field for a single point charge, or 2 point charges, or 3 point charges, or 4 point charges, or 5, or 6, 7, 8, 9, 10. Any number of point charges. You just do the exact same thing. And to do that, we have to kind of use a different formula for the electric field due to a point charge. So you'll see this equation a lot as the electric field due to a point charge, kq over r squared. So if I have some positive charge here, the electric field is a vector that radiates out in all directions. And so if I want to find the electric field here, I would need this r value, and then you could find the electric field there by plugging in the value of the charge, q, k is a constant, 9 10 to the ninth, that's the Coulomb constant, and then this distance from there. And that's fine. It does indeed work. It gives you the magnitude of electric field. It does not give you the vector electric field. So, but once you get the vector electric field, then you have something useful. Because suppose I have two charges. I have a plus charge and a minus charge right there, and I want to find the electric field down here. Well, the electric field due to the positive charge is that way, the negative charge is that way, and then the total electric field would be that way. But I need to find those as vectors. I can't just find them as a magnitude. I have to deal with the vectors. So to do that, we need to have a different electric field equation, and it looks really scary, but it's not. It looks like this. It is scary. It is. I take that back. It is scary, but the scariness outweighs, the usefulness outweighs the scariness. So it's still kq, and it's over r squared, but that's the vector r, and it's magnitude squared. And then we have this other thing right here, r hat. R hat is a unit vector. So we define r hat as the vector r divided by the magnitude of r. And what that does is since we're taking the vector and dividing by its magnitude, we actually get a quantity that just describes its direction. So down here, k and q are scalar values. The magnitude of r is a scalar value, so everything right here is scalar. So in order to get a vector electric field, I'd have to multiply by a vector, and r hat is that vector. Okay, don't worry, I'm going to step you through this. So let's just pick a generic case. And then what I'm going to do is to show you how to do this in Python. And so Python is actually going to make things super easy, but you don't have to. I'm just going to show you. So suppose I have my x and y axis. This is actually could be in 3 dimensions. It doesn't have to be x and y. It's just hard to draw 3 dimensions on paper. And I have a charge right here. Let's call it q. It's some charge. And then I have a vector location of that charge. I'm going to call that rq. It's the location of my charge. And that becomes important because I want to really find the electric field right here at some point O, my observation location, and I'll call that RO. So what I want and what I need in this equation is this vector, R. So you see here, if I know the vector location of the charge and I know the vector location of the observation location, then I have this triangle. And it turns out that this looks a lot like your displacement formula in kinematics. This says that R is going to be the change in position from Q to O. So we can actually write that as R equals the final position, which is the observation location, minus the charge position, RQ. And that is a vector, right? That's a vector operation. Everything's legitimate. And everything works fine. And I can do this. Remember, to subtract vectors, let's say I have RQ is the vector RQX, X component, RQY, that's a Y component, RQZ, Z component, and RO is the vector ROX, ROY, ROZ. Then the vector R would just be, I subtract the components. So the X component would be ROX minus RQX, ROY minus RQY, and ROZ minus RQZ. Okay. And that's that. So once I do that, I need to find the magnitude of this vector, right? Because I'm going to have to find the magnitude squared. So I need to find the magnitude of r, which is just going to be the square root of r x squared plus ry squared plus rz squared, right? Where that's my rx value. It's a scalar. That's my ry value. That's the difference in those, and that's rz. And then I need to find the unit vector r hat. That's going to be r hat is going to be the vector rx, ry, rz divided by the magnitude, which I'll just write as the magnitude of r. Once I do that, all I have to do is plug everything in this equation and I'm actually done. So let's do this for an example. I'm going to pick a charge. It's not going to be at the origin, okay? And I'm going to find the electric field. So here's my xy axis. And let's say I have a charge right here, Q, and this is RQ. So I'm going to say Q is going to be equal to 4 nanocoulombs. R is going to be the vector. I'm just eyeballing it here. So it's a vector. And in case you didn't notice, I'm using this angle bracket notation for vectors. So with angle bracket and then the three components. Let's say it's 0.02, 0.03, 0 meters. And now I want to find the electric field right here at some other location, RO. So I'll say R, that's RQ. RO is going to be equal to 0.04, 0.01, 0 meters. Okay, let's do this by hand, and then I'm going to do it in Python. So the first thing we need to do is to find the vector R. It's just going to be RO minus RQ. Well, I can actually do that without a calculator because I can subtract components, right? If I take 0.04 minus 0.02, I can do that without a calculator. That's 0.02. And same thing for here. 0.01 minus 0.03 is going to be negative 0.02, and then 0 minus 0 is 0. So this is my vector. It is in the negative y direction, just like I said right there. That's my vector r. Now I want to find the magnitude of that vector. R magnitude is going to be the square root of the x component squared, 0.02 squared, plus the y component squared, 0.02 squared. The negatives is negative times negative, plus 0 squared. So let's do that with the calculator. It's not too hard, but that's fine. So clear this. I'll do the square root, 0.02 squared plus 0.02 squared, close parentheses, equals. And I get 0.028. Let's just round. 0.028 meters. That does have units. Now I can find the unit vector r hat. R hat is going to be the vector r right here. 0.02 minus 0.02, 0, divided by 0.028. And that's meters, but the meters cancel. To take a unit vector and divide by a scalar, I have to divide each component by that. So I'm going to take 0.02 divided by 0.028, 0.2 divided by 0.028 equals, and I get it's 7.14 times 10 to the negative 1. So it's 0.714, and then I'll do that for the x, the next 0.02. Oh, it's the same thing. It's the same thing because it's just negative, so I have negative 0.714, and I can do 0 divided by that is 0. It has no units. So there's my r hat. Now I'm ready to put everything in my equation. So E, due to that charge, is going to be K, 9 times 10 to the 9th, times Q, 4 nanocoulombs. A nanocoulomb is 10 to the negative 9th coulomb, so it's going to be 4 times 10 to the negative 9th. And I'm leaving off my units because I just don't want to get too messy. It's already messy as it is. Now I need to multiply by r hat, which is this. 0.714, negative 0.714, 0. And then I need to divide by the magnitude squared, which is this, 0.028 squared. So let's leave that vector alone. Let's just do this stuff first. And that's going to be, because I can do that. I have 9 times 10 to the 9th times 4 times 10 to the negative 9th. So 10 to the 9th times 10 to the negative 9th is 1. And 9 times 4 is, what, 36. Okay, so I just have to do 36 divided by 0.028 squared. So 36 divided by 0.028 squared equals, and I get 4.59 times 10 to the 4th. And I still have that other vector, 0.714, negative 0.714, 0. Now I can multiply this scalar by each component to get my total vector. So I have this times that, this times that, this times that. So I only need to do one calculation. So I already have that number in there. I just need to say times 0.714 equals 3.28. So I get 3.28 times 10 to the 4th. And then I the same thing. It's just going to be negative 3.28 times 10 to the 4th, 0 newtons per coulomb. And that's that. That's my electric field as a vector. And that's important that this is a vector, because if I have more than one charge, I add up all the vectors. Let's switch over to Python, and I will give you the code for this and do the exact same problem. Okay, we're going to do the exact same steps. Okay, so if you're not familiar with Python, I'm just using it as a calculator. I'm not doing any loops or anything like that. So it shouldn't be too scary, but it may be scary, and that's okay. It's okay to be a little scared. Okay, so let's just look right here. This is I'm in GlowScript VPython. This is a web-based. It's Web VPython. This is a web-based Python implementation that has some really useful tools in there. It does have vectors in there too, which is really cool. So let's just get to it. I'm gonna create some variables. I'm gonna say Q equals 4 nanocoulombs, so 4 times 10 to the negative 9th. So in Python, E negative 9 is 10 to the negative 9th. Okay, and then I need my vector location of the charge. So I'm going to call that RQ equals. Now here's the really cool part. I can actually enter a vector in Python. So I can say vector. It's a class in GlowScript VPython, and it was 0.02, 0.03, 0. And then I can enter a vector RO for the observation location 0.04, 0.010. Let's just do something. I'm going to show you print Q equals Q, and I'm going to run it. And there you go. That's what I had, right? I'm showing you that how it works. I can print those vectors too, but I don't even want to do that. Let's find R. R equals RO minus RQ. We already did that, but I had Python do it. So now I can just say print R, oops, lowercase r, R equals R. I'm going to put the units to meters just because it looks nice. And there you go. That is what we said. That is what we said it was R was. Okay. So I can do that vector operation there. And what's really nice is once I do this, I can change these values. I could change this to 2 or whatever, and it doesn't care. It just redoes it. It doesn't care. It's just a computer. Okay. I care. Computers don't care. So now we need to find the magnitude of that vector. Let's call that something. Let's call it Rmag. And it turns out that there's a magnitude function built into Web VPython. So I can actually just say mag R. And then let's print that. Print Rmag equals. You can put whatever you want in quotes. It just prints it out that way. Rmag. And then it would be in units of meters. And I'm going to run that. So 0.028, that's what we had, right? We're all in agreement so far. Now I need to find the unit vector. And again, I could I could say R hat, that's that hat above it means. I could say that's just R divided by R mag. That's what we said. So let's print that. Print R hat equals R hat, and there's no units. Okay, that's a little bit different than when I had 7.14. It's because I rounded. It's okay. Don't worry. It's okay. Okay. Just to let you know, there's actually also a built-in function for the unit vector. I can say print R hat equals norm. You gotta spell it right. Norm R. It should give me the exact same thing. Exact same thing. Okay. So now I have everything I need. I can calculate. Oh, I need K. Let's put that up here. It's a constant. K equals 9 times. Oops. K equals 9 times 10 to the 9th. So now let's calculate the electric field. I'll put it. E equals K times Q times R hat, which is just R hat, divided by R mag squared. So I'm going to say R mag. So in Python, square is star star. It's not the hat. I don't know why. Don't ask me why. That's just what it is. So that's that. Now I can print E equals E, and I'll put the units newtons per coulomb. And so I get something that's a little bit different. I had 3.28, but again, it's because of rounding. But the same order of magnitude, the same sign and everything. So I'm pretty happy with that. If you want, there's one more thing you could do. I could say print the magnitude. Let's say print, I'm going to put it like this. E, so it looks cool, equals. And then E is a vector, so I can take the magnitude of that. I can just say mag E, and then give the units, newtons per coulomb. And so that's the magnitude of that vector. Square both sides, square both components, add them together, take the square root, and that's that. Now, I'll give you this code, okay? But any charge you want to find an electric field from, you just put the value of the charge, you put the vector location of RQ, the vector location of RO, and it's done. I've already done everything for you. If you have more than one charges, you just do this more than once. There are some ways you could make this as a function and stuff like that, but I'm not going to do that today. I just want to give you this and show you how to do that. So let's go up here and save this, because I didn't actually save it. I'll call it any electric field calc. And I will give you a link to the code so that you can do this. This is actually in Trinket.io. You don't need to log in to use this. You can actually edit it and run it, but if you save it, you'd have to log in. It's free. You can log in for free and create an account for free. I find it very useful. It's a great calculator, I think. But hopefully that helps. I'll stop there.